For the next problem, we will have charge Q uniformly spread along X from A to A plus L. There will be charge Q uniformly spread. Uniformly spread from A to A plus L. What we need to find? We need to find force exerted by this charge Q on a point charge minus Q naught located at the origin. So again, we need to slice this charge Q into infinitesimally small charges dq. So this is charge dq located at arbitrary point x, and the length of this infinitesimally small segment is dx. So charge dq located within dx. We can write magnitude, the magnitude of force exerted by this dq on minus q naught. First, let's draw it. This will be attractive force. Again, let me remind you that we find the force acting on minus q naught. So this force will be to the right, and I can write magnitude of this force, or we can write immediately, break this force into components, because we understand that there will be just one component. It will be x component of this force. So force will be along x, and I write dfx. Why df? Because this is infinitesimally small force created by infinitesimally small charge dq. So this force is, according to Coulomb's law, constant k, and then I have product of charges q naught dq. I remind you that we put magnitude of q naught here, magnitude of dq, so q naught is negative, but here is magnitude. Where did I take into account that q naught is negative? The force is to the right, it is attractive force, and projection of this force in x is positive, and that's where I took into account that q naught is negative. So here I have plus. Now I need to write distance between q naught and dq. This distance is x, because dq is located at arbitrary point x, so distance squared is x squared. This force is along x. This is already x component of force. All I need to figure out, what is dq. dq by definition is lambda dx, where lambda is charge per unit length, Since q is uniformly spread, we write lambda as charge divided by length. Length is L. So I bring lambda here. I have q over L for lambda dx, length of this infinitesimally small chunk of charge. And then I can write now dfx and integrate it. So dfx is equal to k, and then q naught. dq is q over L dx, q over L dx. This is dq. And I divide by x squared. All we need to do, we need to integrate dfx. We need to integrate from a to a plus L. Integral from a to a plus L. Constants, I will write constants first. K, q naught q divided by L. And then the variables are right here. It is dx over x squared. We will factor out, we will bring all constants here. It is k, q naught q divided by L. Then integral dx over x squared is minus 1 over x from a to a plus L. This is equal to k, q naught q divided by L. And then I factor out this minus, I bring it in front of k. Then it is 1 over a plus L minus 1 over a. Let's bring it to common denominator. So it is minus k, q naught q divided by L. And then I have here a minus L divided by a plus L. A minus a. I have minus L and minus here, which will be plus L. Then L and L will cancel out. So all I have is k, q naught q divided by a and a plus L. So this is x component of force and there is no y component, so this is our final answer. We found the force exerted by charge q that is spread from a to a plus L on a point charge minus q naught at the origin. Important part is that we choose dq at arbitrary point x. If we choose it here at a, or we choose it here at a plus L, we will not be able to integrate. X is arbitrary. Now, let's consider the situation when this rod is far away, this charge q is far away from charge minus q naught, which means that L, length of the rod, is much smaller than A. So L now is, I will use different color. So we will consider this special situation when we bring this rod far, far away. So L is much smaller than A. Then what do we expect if this charge q is far away? What will be the force? F sub x will be, I neglect L in comparison with A, I neglect L, then I have A squared, and the force will be q naught, q divided by A squared, as from a point charge q as we expected, if q is far away.